I have a love-hate relationship with inverse trig functions. The formulas are tricky to memorize, but it's such a good practice with the unit circle, and they really are pretty useful in life. Let's do an example from the notes, since it might have been hard to follow on paper, but we're going to make it a little more complicated and add limits of integration to that problem. So I have this monster. Now in real life, what happens is you forget about inverse trig functions and you try to solve this using u substitution. If I do that, if I let u equal e to the 2x minus 1, then du is going to be e to the 2x times 2 dx, and I'm going to get stuck because there is no way that I'm going to get this to cancel out of this using u substitution. So I'm stuck, and I have to think, oh right, those pesky trig functions. So I'm going to start over. I'm going to consider my options for an inverse trig function. It's a square root, so it's either going to be arcsine or arcsecant. And what I see is that I have a variable minus a constant, so I'm going to try arcsecant. Let's look at the formula for arcsecant. It's the integral of du over u square root of u squared minus a squared. I need this to match this form. So the trick on this one that I see is that I need this to be u squared. So I'm thinking, how can I get e to the 2x to be something squared? Well, here's what I have to think. E to the x, if I squared that, when I have a power raised to a power, I multiply. So that becomes e to the 2x. Oh, look, which is what I have, right? So what I need is I need to set u equal to e to the x. And this term here then becomes my u squared, right? So this is going to work. So du is equal to e to the x dx. And so dx is equal to 1 over e to the x du. This is exciting. This is where my u is going to come from. So when I go to rewrite my integral then, what I've got is I have the integral of 1 over e to the x times the square root of u squared minus, I didn't look too closely at my constant here, 1 is 1 squared, so my a is just going to be equal to 1. It's convenient. So I have u squared minus 1 squared du. And this almost looks like what I need, right? I need a u on the outside here, and we said that u is equal to e to the x. There's my e to the x, so I can rewrite that as u. This is the integral of 1 over u square root of u squared minus 1 squared du. Okay, this is good. This didn't look, oh, this is a mess now, isn't it? Let me get rid of some of that here. Okay. This didn't look very promising to get me into this form, right? Because I was missing something out here that was going to be my u, right? But the process that I had here is I said, okay, I have a variable minus a constant, and that fits the format of secant, so I'm going to try it, and lo and behold, it worked out. And it's going to in most of these textbook problems. Had it been a constant minus a variable, then I would have gone for arcsine. The other thing that I want to go ahead and do here is I want to change my limits of integration. Anytime I do u substitution, I want to do that. So I'm going to plug each of these limits into this formula for u. So if I do e to the 0, let's change colors there. If I do e to the 0, that's just going to be 1. If I do e raised to the natural log of 2 over the square root of 2, the e is going to cancel out that natural log, and so that's just going to be 2 over the square root of 2. So over here on my fancy integral, I'm going to rewrite those limits of integration, going now from 1 to 2 square roots of 2, or 2 over the square root of 2. So this is 1 to the square root of, mixing that up. There we go, 2 over the square root of 2. Now I'm ready to apply the formula. Looking at my sheet, if I apply the formula, I've got 1 over a, which is 1, arcsecant of the absolute value of u over a was just 1, and I want to evaluate that from 1 to 2 over the square root of 2. Simplify that so it's not as gross to look at. I've got the arcsecant of the absolute value of u evaluated from 1 to 2 over the square root of 2. Remember, you can write arcsecant or you can write secant inverse. This is going to be the secant inverse of 2 over the square root of 2 minus the secant inverse of 1. Now remember how I read this. I read this as what angle has a secant of 2 over the square root of 2. And that's very hard for me to think about the unit circle in terms of secant, right? It'd be much easier for me to think in terms of cosine. So to get from secant to cosine, I can do the reciprocal, right? I could make this 1 over the secant, which means I have to do 1 over this angle. This angle. So if I flip this one over, I can flip this one over. So this can become the cosine inverse of, instead of 2 over the square root of 2, I can make that the square root of 2 over 2. That looks like something on the unit circle. Same thing with the second term. If I'm going to make this cosine, then I have to flip over that 1, which is still just 1. And this is much easier to deal with now. Now I'm asking the question, what angle on the unit circle has a cosine of the square root of 2 over 2? Remember, cosine is asking for the x value, so I'm thinking, okay, unit circle, what angle has an x value, x coordinate, a square root of 2 over 2, and I know that that is pi over 4. Asking the same question here, what angle has a cosine of 1? Where do I have an x value of 1? That's going to be right here, and that's an angle of 0. And so I'm reduced to just pi over 4.